Now, all of us try to hold a bottle and try to impress our friends on making a sound out of that bottle by blowing a strong air on its surface and trying to play with the speed of the wind going through the mouth of the bottle so that we can generate a higher sound. And it's important to know that all the wind instruments, like the flutes and what other stuff like it, are using the principle of resonance to produce music. The simplest example, as we said, of resonance is music is when you blow on the top of the bottle. So you blow across the top of the bottle that will oscillate the air in the bottle and generate a standing wave, like the waves traveling in a spring. But unlike the spring that's fixed at both ends, the air column is fixed only in this case at the end where reflection occur and free to oscillate at the open end. So the resonant frequency of the node produced depends on the length of the air column because to resonate, the standing wave must have a node at the closed end of the bottle and an antinode at the open end. So when you create an oscillating wave, you need to make sure when it hit the surface of or the base of the bottle, the swing back should be an open end. So the you can say like the top of the antinode should be at the mouth of the bottle to be able to create as amplified sound as possible. We can define more what we call as closed tube or closed pipe resonance. When the wave source is held at the open end of the pipe, like the tuning fork in this case, it sends down a wave, will reflect at the base, and it will go back, establishing a standing wave pattern. It will go back up to the top in her oscillation. The sound that you hear depend on the length of the air column in the pipe relative to the length of the standing wave. So how long is the standing wave versus how long is that cup or that bottle? If the antinode occurs at the open end of the pipe, like point A and C in this case, then a point of resonance from constructive interference will occur at the open end of the pipe and sound appear to be amplified. This is known as closed pipe or closed tube resonance. So you can see here when the swing or the oscillation, you hit it here, then your sound wave will go here and hit the base and go back up, but it closed over here. There will be no amplification for sound in the outer medium. But here, it's like the antinode is open at the mouth of the pipe, so it will be louder. Here it will be muffled, and here it will be a louder resonant sound that you can hear. It's important to know that nodes are located every half wavelength, as we know, from the end at which the wave is reflected. Just as they are in the standing wave in the spring, if the pipe length is equal to any multiple of 1 over 2 lambda, there will be a node at the upper end of the pipe and the destructive interference will occur. So when the air column is half lambda, 1 lambda, 3 over 2 lambda, 4 over 2 lambda in length, then that means there will be little to no sound that can be heard or amplified. Let's take an example on a tuning fork with an air column or with a bottle. You have a tuning fork with a frequency 384 Hertz held above an air column. As the column is lengthened, a closed pipe resonant point is found when the length of air column is 67.5 centimeters. That's where you start to get a closed pipe resonance phenomena. What are the possible wavelengths for this data? If the speed of the sound is known to be slightly greater than 300 meters per second, what is the actual wavelength and the actual speed of sound? We have frequency and we have the length of the pipe in this case. Now we need to find the wavelength and speed of sound. Now we said resonant point should be either at 1 over 4 of the lambda, 3 over 4 of lambda, or 5 over 4, etc. for the tuning fork. And we see that 67.5 centimeter is the first resonant point. 67.5 centimeters is 1 over 4 of the lambda. To find the wavelength, you need to say that the length equals 1 over 4 the lambda. So the lambda in this case is 4 by L, and that would give you 2.7 meters as a wavelength. And we can see the velocity equals frequency by lambda. Frequency is known and lambda is known by this case. You will get 1037 meters per second of speed. Now this wavelength is larger than speed of sound in air. If the speed of sound is not of the proper order of magnitude, then assume that the resonant point is the second point of resonance. That's 3 over 4 lambda. Find the wavelength again. Length equals 3 over 4 by lambda. Lambda equals 4 by L over 3. That would be 0.9 meters. V is frequency by lambda. That would give you 346 meters per second. So this is a reasonable speed of sound in air because we know the speed of sound is almost 300 meters per second. So we can complete the analysis for the next phase, which is 5 over 4 lambda. That could be a resonant point. So we say L equal 5 over 4 lambda, and lambda would equal 4L over 5. That would give you 0.54 meters, and the velocity would be frequency by lambda. That would give you 207 meters per second.